Sure, yeah, and I'll be brief. So yeah, today we have a lot of several talks on the use of LLMs in Odyssey lined up. It's very exciting to see so many people working in this field, and we also noticed that, for example, the European Symposium, I think there were 10 independent abstracts on the use of generative AI. So it's very exciting to see so many people working in this space in Odyssey, but it also brings a opportunity, I think, to create synergy. We can start working together a little bit more. And so for that, I encourage you to join the Generative AI and Foundational Models work group in Odyssey. So this is a work group that's already been around for almost a year now. We have our meetings on the second Tuesday at noon, second Tuesday of the month at noon. So right after this call, once a month. And so some of the things that we could achieve by working together is, for example, building shared infrastructure. And you'll actually hear Rowan Perry probably talk about this in a few minutes. And also sharing gold standards, I think would be a good thing that we could all collaborate on. So yeah, with that, I'd like to kick off this meeting, but please think about how could we also start working together more in this space. And please use the work group as a possible way to achieve that.
Great, thank you, Martijn. Since we've talked a little bit about work groups over the last 10 minutes, I just threw the link to the work groups page in the chat. I know everybody doesn't have access to it, but it's odyssey.org/workgroups. Not only can you learn about work groups, but there's a link to join any work group. It's really easy. Quick little form will get you into the Teams environment. That's where meetings happen, file sharing, chat, everything that you need to be part of that work group. So please do check out that page. Okay, we have presentations coming from all over the world. There's some that I have slides, there's some that I have videos, there's some that are just going to present on their own. Some people need to go early, some people need to go late. So I'm going to try to keep this as organized as possible. We're going to start with Georgie Kennedy, and after that, it's going to be Olga Endrich, and then I'll go from there. So Georgie, you want to start?
Yep, great, thanks, Craig. I'm just going to share my screen, although something weird seems to have happened now. Sorry about that. Hang on. Here we go. Does that look right?
Yes.
Okay, cool. Okay, yes, so as Craig said, we're kind of speed running today. So I thought that the easiest way to orient the work would be to start with the key functional requirements that I'm working towards. So just in summary, obviously, stable semantic grounding of extracted concepts is what we're all looking for. But I think more importantly, the ability to enforce constraints, not just for individual concepts, but across the entire extracted record is really important. This work is prioritizing a sharing first development pipeline. And I think while zero shot is definitely not the answer to all use cases, if we start there, it supports the engineering of a really thoughtful solution before we add complexity only when it's actually required. And through that, hopefully the largest universal uplift. I've prioritized small model use for a few reasons, rapid prototype generation, democratization of access, and ideally kind of lowering the moat that's claimed by a lot of enterprise solutions. And also just noting that I need to accommodate in this solution very significant environment limitations as well. I reviewed onto GPT in depth because it was very promising for these requirements. It's based in SPIRES, or structured interrogation and recursive extraction of semantics. Broadly speaking, conceptually, it's a good fit, but significant practical roadblocks to getting working. Given the limited time, again, I think I'll walk through each of the roadblocks and how it was solved, because I think that gives the most rapid overview of the delivered solution. So SPIRES is based in LinkML, which is the YAML-based data modeling language. Very extensible. You essentially build complex expressions by combining simple base elements. And when interrogating the LLMs, the LinkML definition is used to generate the structured prompt, as well as validate the actual data that's returned by the model via the LinkML runtime. LinkML is also really useful for things like order documentation of conventions, as well as the creation of shareable ETL unit tests. But for now, just note that it generates Pydantic classes natively. And the first step in making this work was to create the LinkML expressions to capture the way that OMOP conventions are typically actually defined. Essentially, we need to go quite a lot further beyond the capacity to specify static concept enumerators and instead use dynamic relationships. And this example shows the expression required to constrain a response to a specific domain, just as an example. Their implementation was actually quite brittle because it parsed a kind of pseudo YAML. So this was replaced with the instructor library. I think that this is the right LLM abstraction to bet on. Most good options are already backed by the Pydantic ecosystem under the hood, and this one just happens to be the one actually created by that team. It also means that it integrates with just about anything you can throw at it. The OntoGPT implementation uses bioportal ontologies by default. These do have some of the OMOP vocabularies available, but it obviously misses out on a lot of the richness that's available in the full specification.
Georgie, I'm just going to interrupt you for a second. Your slides don't seem to be moving.
Oh, really?
Yeah, we're still on the...
Working?
No, if you want to just make sure you send me your slides after, I'll put them on the page.
I have a link. I have a link. This is not going to make much sense without all of the things I was talking about, though. I was really relying on the visuals because we had to go so fast. Anyway, that's okay. I will send a link. So there was a lot of stubs around for converting Athena files into OWL, but none of them let me get a sort of low enough level to encode all of the necessary factors. So I did end up rolling my own converter. I've linked to that at the end, but again, you're not going to be able to see that. But we convert those to SEM-SQL, which pre-compiles predicate flattening queries to make ancestry traversal a constant time function. And finally, I had to adjust the grounding steps to handle the updates to the LinkML specification that I showed but didn't visually show earlier. So I can't show you this thing, so it's not going to make any sense, but essentially changing the grounding steps allowed us to combine the basic building blocks into complex convention expressions, which means essentially we're forcing the LLM to return values that conform to actual structures and relationships, as well as the semantic grounding that we're looking for. You won't be able to see the results that I'm talking about. And so if I've lost you in the rapid fire, the key takeaway is that once the pipeline is up and running, for every new NLP target, all you have to do is to define a LinkML template, such as the one you can't see, and the rest of the solution remains exactly the same. So we can basically create a growing shareable library of definitions. And in terms of the current focus, I'm working on securing the optimal hosting of the solution. And then I have a bunch of links. I will send a link to this in the chat, and that will be a lot easier, I think.
Oh, that just, something just popped up there. So I'm not sure if, yeah, I can see the slides at the bottom, but they just didn't run through. Right. Georgie, you mentioned you wanted to share just a couple slides. So let's see if you're able to do that.
Sorry, I did work out why that happened. I updated my Mac OS while I was waiting for the call to start, and I had a permissions window that I didn't click before I started sharing my screen. So at least I worked out why. So now I believe you're going to be able to see it, even though I'm not actually just sharing full screen.
Yes.
So just to whip through a couple of key things that I think will help people understand what I was yammering on about. This is the library that I was investigating. So OntoGPT, it's fine, but needed a lot of work to get it done. This is the overall workflow. Again, these slides are linked, so I won't go through it again, but I wanted to just share, I guess. So this is an example of the LinkML files that I started to work up. And I think that there's a lot more to the LinkML ecosystem than just LLMs. So I really want to kind of dig into that on general data validation and unit tests as well. But this is kind of what it looks like. And I think the really important things to show. So this is the library for generating OWL class files. And just to explain what the SEM-SQL is, because I think that this could be plugged out and put into a lot of different solutions as well, because it actually makes the whole parsing of the ancestry a lot faster as well, because it basically pre-generates all of the predicates, making it a tractable solution in real time. Then the other one that I wanted to just really highlight, these are the results that we got. I'm not clinical. It did a lot better than I could do, which I think is the most you can ask some of these things. And then this is the key element here, which is if you create a new definition file that looks essentially like this, you can keep your pipeline in situ and just kind of swap out the definition files to get a whole new LLM target into your pipeline. So this is a bit where it's, kind of, you don't have to redevelop anything to get new outputs. And this is the hosting solution that I'm looking at the moment. Ramalama is great. I recommend looking into it. It auto detects your hardware to ensure that you have an optimal solution, but also importantly in a secure environment, it integrates with secure model backends. So in combination with Podman, it is a secure kind of complete solution for the hosting of that. And then these are all the links that are in the slides that if you want to read it in more detail. Anyway, thank you for letting me try again.
No problem. Thank you for doing that, Georgie. We're going to go to Olga next. Olga Endrich. There we go. Okay. You are mute. I'm not sure if you're talking, but you're muted.
Okay, can you hear me?
Yes, I can.
Okay, thank you. Thank you very much. I would like to present our framework for cross-lingual medical intervention terms analysis tool. The name is MapCare, and we developed this for the reason that we want to make classification of medical procedures, surgical procedure, interventional, interoperable. So we are in Switzerland, and in the majority of countries, there are medical procedure often country or healthcare specific. So this classification are only available in local language. They're often multi-axle, they include abbreviation, and they are really difficult to make interoperable. And semantic mapping or keyword search are always challenging or misleading. So we thought it's something has to happen, and we started this project. We took our Swiss classification. This name is CHOP, Swiss Operation Procedure Catalog, and it's available in 3 languages, in German, French, and Italian. We also took the Operation Classification Procedure Catalog from Germany, which is available in German. So both are not interoperable yet, so they are not also translated to SNOMED CT. There is not official translation of these catalogs, and there are some point anachronistic thing which is still in use, at least in our country. So what we did, we developed a MapCare framework. We're starting with the input of classification in non-English language. Then the next step is data sanitation, and we use LLM Gemma 2. They provided machine translation augmentation. So actually, in this step, a lot of transformation of the terms was proceeded post-processing. We created a vector embedding in ChromaDB, and at the end, this classification was stored as a vector in a vector store space. So this MapCare workflow is generalizable, so I think it can be used for different languages, different classification. It can be run on CSV file, and we also provide a link to a GitLab in this publication, so it can be used open source. To use embedding space, it's in our use case, we loaded both classification, German and Swiss one. So we can load catalogs, we can search them in English, so using the English terms, and retrieve both Swiss, CHOP, or OPS terms from the embedding space. We also validated the quality of the translation. We use OHDSI tool in our environment also for development of the semantic layer in our clinical data warehouse, mainly using for alignment between different EHR systems. We also used OHDSI tools for translation of surgical procedures to SNOMED CT. This manual work was validated by our team, and these are the results. So for the multilingual translation between German, French, Italian, and English, you can see the matrix on the left side in green. So it works really well. If you take mapping results for the top 5, so some languages are better comparable, for example, French is target and Italian, but still we have, I would say, not bad results for this translation. And we also validated the quality of translation mapping for SNOMED CT, making different levels of quality, equal, equivalent, exact, narrow, and unmatched. You see the results on the left side. So now we are planning to use it more for our different cases, and I think it's a good starting point. Thank you.
Great. Thank you, Olga. Next up, I'm going to have Joel go, and then I'm going to run slides after that for, and forgive me for mispronunciations, Zsolt, Jianlin, and Rowan. So Joel, you'll go, and then we'll run slides, and after that, it'll be Iurii Iurchenko. Okay.
Okay, so let me share my screen. You can see it, right?
Yes, I can.
Okay. So what we want to do was to try using LLM to create concept sets for some of our studies. I want to walk you through the steps in the process that we used. We start off with a list of suggested concepts and its descendants. So we start off with a health condition, for instance, right heart failure. And we look in the vocabulary and we come up with a reasonable concept ID to start off with right heart failure. So we took that right heart failure and all its descendants. Then we add in all the recommended concepts from Phoebe for that concept and its descendants. We get a longer list. And then we pass that list to the LLM for analysis. We then parse through that list of the LLM results for what it said should be included in a concept set for, in this case, let's say right heart failure. And we create a second list of the concepts selected by the LLM, and then we add in their descendants. So Phoebe added, if the LLM selected some things from Phoebe that weren't in the first one, we now will check that new list plus their descendants. So it adds in quite a bit more. We then pass that new list to the LLM for analysis, parse through the list of that for the second time, and now we get the list from LLM from all the selected concepts that the LLM said suggested should be in the concept set. And then finally, we post the concept set to Atlas. The input for this is fairly straightforward. Just a few concepts. The main ones to look at is the concept name, for instance, let's say right heart failure, and the original concept list. This would be one or more concepts that are associated with it, depending on how deep you want to dive into the concept. So you can put in as many concepts there as you want, and then like I said, it'll take that and its descendants. It also gives you ability to do excluded conditions. So if there's something that you wanted to exclude from that concept set particularly, you can do that. And then it provides you the way to give the output. This is part of the prompt, but this sort of gives the idea of what we're looking for. We asked the LLM to say if the concept, if the suggested concept in relationship to the main concept, let's say right heart failure, is in that 95% or more of the patients with that suggested concept actually have the main concept. So in this case, if greater than 95% of the patients with right heart failure, with right ventricular failure with sepsis have right heart failure, we would want to include that. But we ask LLM to give arguments for each of these different cut points. So if it's rare, less than 10%, common 10 to 90%, very common 99 to 95%, and like I said, ubiquitous, where the LLM says that probably 95% of the patients with this suggested code have the main code. So that's what we're using as the cut point for this, to be able to include something in a concept set. So far, the results look pretty promising. We've tested on at least 100 different health conditions. We've looked at chronic health conditions, acute, symptomatic health conditions. A lot of times, we're in some of the anecdotal testing, some more formal testing, that the concept sets are very similar to those that are produced by experts doing this. The other thing that it does is that we have the LLM give the rationale for why it wanted to include something in the concept set. And a lot of times that rationale, when looked at by experts post hoc, and said, yeah, we probably should have included that concept set in there. So it gives a little extra detail besides just saying yes or no whether something should be included or not. That's all I have.
Great. Thank you, Joel. Let me pull up the next set of slides. I know that people have questions. Let's try to use the chat as much as we can for this, so that we can make sure we give everybody a chance to go. I think it is this one. Okay.
Yeah, that's me.
Yep, go ahead.
Hi, my name is Zsolt István. I'm from Hungary, from the Szemmelweis University. Thank you for the sharing the presentation. So basically, we, in our CDM, we have a lot of structured information, but to be honest, I don't know, 70% of the information is in the free text. So we tried to, let's say, a pilot project for developing a tool for extracting the data from the free text. Basically, the idea was we have an ongoing project, diabetes, where we had to create a cohort with 13,000 patients. And for those patients, we have to extract a lot of information, like the blood pressure and the, I don't know, so anthropometric smoking status, family history, stuff like this. Something about 30 parameters. And doing this by hand for 30,000 patients it's insane. So we tried to use the LLM for this reason. On the left side, this is another thing that, as we are Hungarians, we don't speak or write, at least English. The documentation we write Hungarian, so we had to use the LLMs in our own language. And to be honest, the medical Hungarian language is some kind of mixture of English, Latin, Hungarian, so insane, full with misspelling, abbreviations, anything you can imagine, and it's extremely redundant. So a lot of times the doctors just copy together a lot of information in the discharge letter or in the report. So so it's not an easy to process these even by human mind. The next slide, please. In this slide, I would like to show you the workflow what we have used. What we have done is to create it, let's say, a manually created golden set for something about more than 1,000 documents, and we processed it by hand by medical doctors, medical students and doctors, extracted the information, and this was some kind of golden set we used later for validation of the large language models data extraction. So in the next step, we had to create some kind of pre-processing, as I told you that the documents were redundant and had other problems. With this step, we were able to reduce the lengths of the documents by almost 40 or 50%, which it goes because makes the whole process faster and cheaper in that way. The next step was the prompt engineering, and then we extracted the information with 4 models because we wanted to test the different models' performance. Actually, we wanted to use on-prem models or models which could be used on-premise because of the GDPR and other let's say Hungary regulation. We not allowed to send out the patient's documentation to the cloud. So at the end, the next step, the next slide, please. At the end, we achieved quite good results. The most important thing is that we were able to find the best model for testing this data extraction, and the parameters we wanted to extract are not important. The important is that we were able to test that the different types of data parameters like numeric and list and booleans needs different models, and based on this information we choose the final model. The next slide, please. And it was Quan, and we use this to extract the data. And so at the end, we were able to extract these 13,000 patients, I don't know, 100,000 documents with LLMs with quite a good accuracy. We're very happy with these results. And this was only a pilot project. We would like to go on and create some kind of general solution for extracting data, and after that, for sure, putting it back to the OMOP database for later the other research project as well. Thank you very much.
Great, thank you, Zsolt. Next up, Jianlin.
Hello, I'm Jianlin from Jianlin Shi Research. Here I'm presenting automatic LOINC document ontology name entity recognition for clinical node titles. Next, please. So the motivation of this study is originated from our needs that when we're doing NLP research, we often need to find a certain type of node titles based on node titles, but the titles was not standardized. And sometimes people just start to create their own node titles without explicitly saying the meaning of that. So we need to come up a way to standardize node classification for more reliable node filtering or node selection. And LOINC document ontology is one of the standards that's being relatively widely used across EMR and supported by OMOP CDM integration. Next, please. A little bit explanation, introduction about LOINC document ontology access. As you can imagine, that there's a lot of ways people can describe node titles. In order to standardize, this ontology describes node title in 5 key access, kind of document, setting, type of service, etc. And each of the access can be matched to a set of LOINC code. So this study, if we are focusing on the first step, try to identify these 5 key access from node titles. Next, please. So we annotate the 1,000 annotated node titles, and with double check with a second annotator and adjudicate the difference. Annotation schema we aligned with this ontology access. We tried supervised learning based on BERT model and unsupervised learning using large language model. As you see, we tried 2 different large language models here because this study was done last year, so it's not the latest large language model anymore. We're using name identity recognition measurements to measure the performance. Next, please. As you can see here, supervised learning still performs the best at this point, but unsupervised learning still reach relatively good performance, given the task was really challenging because we are only looking for a node title for the node title classification. Next, please. The implication for the applying in the OMOP space is that NLP can potentially automatically mapping the standard vocabulary supporting the OMOP node type concept IDs. And large language model, even it's not performed the best, but it's overall adaptability and potential to use across institutional generalizability. During the error analysis, we find that some challenging cases like acronym ambiguity, and there's also ontology limitations because the ontology doesn't cover all the cases. Also, some of the node title was too ambiguous, doesn't give us enough context. We need to probably include more metadata or even content of the nodes to make the correct classification. Next, please. Already I have covered the annotation. For the future next step, we're planning to integrate node content metadata and probably test more recent models and map to the exact LOINC codes. That will be the second step. and to enhance ontology for OHDSI use cases, because we have observed that sample ontology will not capture most of some of the node titles that we see in our data set. Next, please. This research was funded by putting data to work for reference. Thanks for the authors and also our Menchie NLP team members. The publication, I put a link over here. If you're interested, feel free to check it out. Thank you.
Thank you. Next up is Rowan Perry.
Hey, so my name is Rowan. I'm coming at this from more of an IT perspective. I'm not a researcher anymore, I'm an IT guy. And basically, I want to talk about an enablement project that we've started at the Erasmus University. So we can go to the next slide. So basically, my initial goal was not any research question at all, but basically to try things out and see what we can do and have some fun. I started this together with Adam Black about a year ago. If we can have the next slide. And what we did was we built a semantic search engine, which is quite similar to what the MapCare is doing with the embeddings. And we put that online and we're like, okay, we showed at the European Symposium. We read the program for the European Symposium, like, okay, there's lots of people doing this. We need to add something else. So go to the next slide, please. We're like, so what else can we do? There are going to be more questions, more deeper things. We decided we're going to build a model context protocol server, which is sort of a standard way for LLMs to interact with external APIs. And we hooked it up to Claude, and then we could answer some more questions during the symposium. So we go to the next slide. So we had Tom come by, who was also interested in clinical notes, and he typed in an example and asked the LLM to find the standard concepts, and it then uses the semantic search in combination with its own knowledge and returned some nice results. To the next slide. And Danny came by and he had been struggling with iodine contrast or related procedures, and he said it was giving him a real pain, and we asked them to do that in combination with the semantic search, and it also worked out all right. So we go to the next slide. So we go, well, so after we'd shown this, I was talking to Peter from the Erasmus, and he was like, you know, we have 10 tools doing exactly the same thing. Maybe we should think about consolidating something. We know a mapping tool, whatever, we should start thinking about consolidating all this stuff. So I go to the next slide. Basically, my idea is there's the fun things we do with our models, right? We build agents, we're creating concept sets, you know, we're doing the mapping tools, all this kind of stuff is fun. And under the hood, we actually need a lot of the same stuff. Yeah, so we're either going to need APIs which access certain databases, we're having embeddings, we're having embedding models. So even just to generate the embeddings that we're using in our search engine, just to run the code, it took like a whole week, you know, like there's no need for everybody to generate 6 million embeddings by themselves. So my idea was we could start to, you know, maybe offer some shared resources or shared knowledge, or even just some download files to get this basic stuff in a way that can be used by the entire community. And on top of that, we can all continue having our fun, you know, like it's nice if there are lots of different people experimenting with concept set creations. We don't all need to do all the grunt work. So we go to the next slide. So the last month I've been busy with that. So we've set up a GitHub repository. I've put my embeddings there for everybody to download. Well, they're from OpenAI's model, but you know, anybody can download them and load them into their own database. We've also set up a database which you can access if you like. If you send me a message, I'll give you credentials, so you don't have to do that yourself if you don't feel like it. And also the API that I'm using on my own search engine is also documented and available. And I've also made the MCP server publicly available. Now, this is all the things I've done, but obviously there's no need to just have one of everything, right? We like, you know, multiple people, multiple views, so there it can be expanded and improved upon and all that kind of stuff. And also something that I haven't set up yet is an open source embeddings model. So this is something which would be nice if somebody has a good recommendation. So we go to the next slide. So I think it should be possible to consolidate on some of this basic groundwork, but you know, I'm not going to do that all by myself. So we're going to need feedback, suggestions, sharing of data, constructive criticism. I don't like harsh criticism, so constructive, please. Basically anything that you think could be of value to create like a community capability. Because now I think it's a lot of individual capabilities. I think it can be something that the OHDSI community can do as such. So this is what I'm busy with the coming months, probably. If you feel like you can contribute, you can check out the repositories or send me a message. So not an academic presentation, but a call to collaborate on these kind of lower level things if you're interested. That was it.
Great. Thank you, Rowan. Okay, next up is going to be Iurii. We have a video. Is there anybody else on here that emailed me that they were going to present and I haven't mentioned them yet? I do have 3 from Chan's lab in Korea, but put your hand up if you reached out to me earlier. Nice. Okay. I'm a little more organized than I thought. Okay, Iurii, go ahead.
Yes. Hi, everyone. So I am a senior software engineer. I am relatively new to the OHDSI community. So we were closely working with particularly OHDSI CDM model in industry, building like industry solutions for that. So my current pitch is I am starting developing a tool. So this tool, I call it auto cohort. The goal is very similar to like colleagues presented before. So the main goal is, as far as I see it, it's to like lower the cognitive load from the researcher by implementing AI. So this is the typical workflow like we have in Atlas, for example. Like we are like typically what we are doing is setting the goal, then we're creating a concept set, building cohorts, and run the evidence building. So this is, for example, how looks like the current workflow in Atlas, like I mean process flow. Like we are like setting the goals, then we do all this stuff, and then we generate the insights. So my goal here is to take this middle block and like a little bit automated, I would say. So the architecture of the solution I am currently starting building is like this. You see my screen, right? Just to be sure.
Yeah, I'm seeing your screen.
Good. So the current architecture I see is like the following. So we have operator, researcher, we have user interface. We have a bunch of agents, and as Rowan told before, like he played a lot of that, and I'll be very happy to connect with him and discuss deeper because my goal is very similar. So I'm building agents. Ideally, I gathered some feedback from some community members. I want to do this with the local LLMs. That will be a challenge to pre-train it in a proper way, and then gain the maximum accuracy from them. So this is the example how it may look like on the technical level. So I built a visual prototype of the solution. So it may be found, I mean, the visual prototype right here. That's what I'm doing to implement on the technical level. So if you have chance just to check it out and give me some feedback to this email, I'll be very grateful because my strength is engineering part. So as Martijn told, like our goal is to build building blocks. So that's my goal as well. I want to build building blocks. So yes. So that's the current work I'm doing. I hope I will have some success in the near months. Thank you very much.
Great. Thank you so much, Iurii. I have, there's 3 more presentations that came from Chan's team in Korea. This is about 11 minutes. It's going to go slightly over the hour. So if you have to leave, the videos will be posted later. I'm going to play this now. If you presented today, thank you. If you did not already send me your slides, please send them so I can package them all together for our community calls page. I will wrap up when this is done, but for anybody who has to leave at the top of the hour, I wanted to say that. Okay. Let me know if you don't hear sound here.
Hello everyone, I'm Subin Kim from Yonsei University in Korea. I'm currently working in Professor Chan's lab. Today I'll briefly introduce how we applied generative large language models to populate cancer data from unstructured EHR. The oncology working group proposed valuable CDM extensions, but in practice there are still many challenges in implementing the oncology CDM, especially using EHR data. The biggest issue is that cancer-specific information is often unstructured. They are usually found in narrative clinical notes like pathology or radiology reports. This makes it difficult to extract and standardize the oncologic data. To address these challenges, we introduced an NLP pipeline that applied generative LLMs to extract cancer-related information from unstructured clinical notes. The pipeline consists of three main steps: parsing, extraction, and structuring to the OMOP CDM. For the parsing and extraction step, we use LLM's Gemma 3 to process the clinical text and extract cancer-specific information. Let me briefly explain the parsing step. In this step, we classify the entire pathology report into 4 domains: findings, lymph node, biomarker, and others. This semi-structured format could help extraction step much more stable and reliable. Next is the extraction step. Before we begin the extraction process, we first need to define which clinical variables to extract. As a baseline, we referred to the CAP cancer protocol, which provides standardized reporting elements for pathology. We extracted the cancer-specific modifiers like depth of invasion, dimension of tumors, and biomarkers as a JSON output using generative large language model. And then we convert the output JSON files to tabular format. This makes it much easier to map the data to the OMOP CDM. We randomly sampled about 100 cases for each cancer type and ran our pipeline. We can see that models showed considerably high performance across 3 types of cancer. After structuring the extracted data, the next step is to map each value to OMOP standard concept. For example, a term like adenocarcinoma can be mapped to a standardized concept ID. For each variable, we first determine the appropriate domain and vocabulary. After that, we created a mapping dictionary that links all possible outputs to the standard concept ID in the OMOP CDM. Now we are currently in the ETL process. First, we store these extracted data to Note NLP table, and we link these results to the measurement tables. However, we have encountered some ambiguous cases during the ETL process. Since there are no clear conventions for handling these situations, we plan to summarize our approach and reach out to the Oncology CDM Working Group for further guidance. Thank you for your listening.
Hello everyone, my name is Sumin Lee from Yonsei University College of Medicine. Today I will introduce 2 frameworks for making LLMs more trustworthy and explainable in healthcare: clues for phenotype validation and ArcGAP for standardizing radiology terms. First, clues. Phenotype algorithms define patients using diagnosis codes and clinical data, but they must be validated to ensure they capture the right patients. Manual chart review is accurate but time-consuming and subjective. To address this, we developed Clues, a staged framework recently published in JAMIA. Clues has 3 stages. Stage 1, zero-shot ensemble inference using the LLM's pre-trained knowledge. Stage 2, few-shot refinement with high-confidence examples. Stage 3, manual chart review only for the remaining uncertain cases. At each stage, uncertainty is quantified and only reliable results are adopted. As a result, the need for manual review was reduced to only 25%. Across all stages, low uncertainty cases consistently outperformed high uncertainty ones, and overall accuracy improved through the staged design. Looking ahead, we plan to expand clues to other diseases and datasets, and to use the OMOF CDM and keeper profiles to improve consistency and reliability. Now, the second framework, RK. Hospitals often use their own imaging procedure codes, which makes data reuse difficult. Manual mapping is slow and irreproducible. To solve this, we developed RK, an automated framework using the low-ink RSNA, radiology playbooks, LLMs, and RAG. RK works in 4 steps. Build a knowledge graph, convert local terms into structured JSON with LLMs, and retrieve the top 10 candidates with RAG using weighted attributes, and let the LLM choose the final mapping. This ontology-driven process ensures both consistency and explainability. This study will also be presented as a poster at the 2025 OHDSI Global Symposium. In experiments, RK effectively mapped procedure terms to low-ink RAG, often outperforming the silver references. With weighted matching, it achieved 62% accuracy and a top 5 hit rate of 0.68. Future directions include expanding RK across multiple institutions and domains, refining matching strategies with advanced prompt engineering. We also aim to collaborate with the OHDSI Vocabulary Working Group for international standardization. In summary, clues enables trustworthy phenotype validation through staged uncertainty management, and RK achieves ontology-driven terminology standardization in radiology. Together, they show how LLMs can be applied in healthcare with both transparency and reliability. If you are interested in collaborating, please feel free to reach out. Thank you for your attention.
Hello, my name is Hanjae Kim from Yonsei University College of Medicine. Today, I'd like to share our team's recent work on developing a prototype called Theseus, which helps researchers generate strategic scripts using Atlas and a large language model. As many people here already know, Atlas is a web-based tool for designing observational studies with GUI. And Strategus is an R package that creates a single JSON document specifying study designs, which can be shared for network studies. Basically, the best practice in designing network studies is to define cohorts in Atlas and handle the rest using Strategus. However, Strategus requires knowledge of R and HADES modules, which leaves a gap between Atlas and Strategus for researchers without programming expertise. And we thought that it'd be helpful if researchers could create Strategus scripts with a simple click of a button in Atlas. So we developed a prototype application called Theseus, which is modeled on population level estimation tab of Atlas. This is a demonstration video. This is how Theseus looks like. Just like Atlas, you can configure cohorts and analyze settings here. You first need to set up cohort settings. And this is a mirror prototype, so you need to manually type cohort IDs defined in Atlas demo. Next, to configure analyze settings, you can manually click each item just like Atlas. But here comes the first key feature of Theseus, that you can convert free text study descriptions into UI settings. These are the text extracted from this Ticagrano versus Clopidogrel studies paper. If you click a button, the large language model converts text into structured settings. It provides an explanation on how the settings are configured. And you can also compare the new specifications with the previous version before rendering them in UI. Once your study design is complete, you can export your entire configurations into executable Strategus strategos are scripts. Which is the second key feature of this use?
So to execute the generated script, you only need to copy it into create Strategos analysis specification file in the Strategos study repository template. We used GPT-5 API for this prototype, and it seems that it sometimes fails to completely understand complex descriptions when converting natural language into study configurations in Atlas. But when it comes to generating Strategos codes, GPT-5 shows excellent performance. Except that there was one issue that there is a typo in this function called create empty analysis specifications. And GPT-5 sometimes corrects the spelling automatically, which causes an error when running the scripts. Thank you for your attention, and please feel free to contact us if you have any questions.